Okay, Gauss's law. So we're going to look at Gauss's law. Again, we've already introduced the concept of electric flux, and as we see right here, here's your electric flux on the left-hand side of the equation. Gauss's law says that the electric flux that passes through a particular surface is equal to the charge enclosed by this surface divided by this little character right there, and that is the permittivity of free space. It's 8.85 times 10 to the minus 12 coulombs squared divided by Newton's meters squared. Now, this little epsilon zero right here is actually related to the electrostatic constant. It's sort of the inverse. There's a 2 pi or a 4 pi difference between the two. I can never remember. I always have to look up all these constants. But you know, sometimes you'll see Gauss's law expressed as some constant times k, e times q, and then you know, without this little permittivity constant right there. But either way, it's fine. So what we see is we see the electric flux is equal to basically the amount of charge which is contained within the surface divided by this constant right here. The surface itself is really, in many cases, imaginary, and the flux is what's passing through that surface. So in this particular case, what we need to do is define whatever surface we're dealing with right here and decide how much charge is within that. The shape of the surface, for many of these problems, are going to have a very specific symmetry that is going to allow us to reduce the problem. So once again, this side of the equation simply becomes the product of the electric field times the area. So one of the real keys to Gauss's law is to choose a particular symmetry, make your imaginary surface to match that symmetry, and you can actually calculate the electric field very easily. Again, going back to the previous chapter, we have to remember when we're dealing with two-dimensional and three-dimensional structures, that required us to do some rather difficult integration. And here, we're actually using an integral to avoid that type of integration. We're using symmetry to reduce this integral into something that is very, very simple. Simple product. Now, again, here's a closed surface S. It surrounds some charge Q. So if we look at the electric flux right here, okay, it is equal to the integral of the electric field dot dA, and in this particular case we have a spherical symmetry that's going on right here. So therefore the surface right here, okay, has the electric field perpendicular to it all directions. So in actuality, this would simplify to a very simple relationship where you'd have the electric field times the area equal to Q divided by epsilon naught. Okay, so again, Gauss's law: pick your surface, enclose whatever charges are there, and the flux is going to be equal to Q divided by epsilon naught. Okay, we'll get back to the spherical symmetry a little bit later. Let's look at some cases where we don't care that the electric field varies over the surface. We're just interested for some, very general surface, what the electric flux through that's going to look like. Okay, so here's some basic cases, and they illustrate very nicely what Gauss's law is about. In this first case, A, we have a charge which is outside a closed area. Don't know how well you can see this, but basically this area is wrapping around some volume in space, and the area is closed, there's no holes in it. So basically, when we look at the electric fields passing through this, we know that at small places on the surface, the electric flux is not zero. But Gauss's law is talking about the total electric flux. So here, we have a negative electric flux because an electric field line is going in. On the opposite side, we have that same field line passing out. So this out versus this in, this negative electric flux at that very small area, plus this electric flux going out cancels out. So clearly, any electric charge which is outside the surface cannot contribute to the total electric flux of that surface. Why? Because the charge being outside the surface has a field line going in, but what goes in must also come out. Okay? Same thing for this field line right here, same thing for this field line right here. These three negative field lines and these three positive field lines cancel out perfectly. Okay. What about the case of the dipole? Now, clearly with a dipole, we have charge enclosed inside the surface. Okay? Here's a positive charge, here's a negative charge. We're assuming this is a dipole, this is an equal dipole, so the positive charge and the negative charge are equal and opposite. And, well, let's examine that. For the positive charge, we have the field lines passing out of the surface, okay? But we also have field lines going into the surface from the negative charge. Because these are equal and opposite, this charge plus this charge equals 0. And by Gauss's law, the field lines leaving the surface due to the positive charge are going to be positive or create a positive contribution to the electric flux, are going to be canceled out by the negative flux from this negative charge right here. Finally, we have our case where we have different surfaces, S1 and S2. S1 is a smaller surface, S2 is a larger surface. Both of them enclose a single positive charge. Thus, the electric flux, the net electric flux, is going to be positive. Regardless of how big that surface is right there, that surface is going to have the same number of electric field lines leaving it, and therefore the total electric flux is going to be the same for the small surface and the large surface, because by Gauss's law, the total electric flux is proportional to the amount of charge enclosed. Both surfaces enclose the same amount of charge. Okay, last case right here. Here we have a surface S. It encloses 3 of the charges, but doesn't enclose some of these other charges right here. How do we calculate the electric flux for this case? Well, once again, we do it by taking a look at how much charge is enclosed and dividing that by epsilon naught. Okay? This is really, really simple, right? And this is actually very much like some of the homework problems that you have. Q1 is right here, Q2 is right here, Q3 is outside, Q4 is outside, Q5 is inside. We take the sum of all the charges divided by epsilon 0. That's how much electric flux leaves us. Now it's very important to point out that this is an irregular surface. This is a surface whose symmetry does not match the symmetry of the charge distribution. So what you're going to get on this is, on this side the electric field line is going to be pointing inward, and on the top side the electric field line is going to be pointing outward. So certainly you can calculate the electric field based on the electric flux. All you're getting, the only information that you're getting here, is how much flux, the net flux out of the total surface. Okay? So you can get flux from this, but unlike some of the later problems that we're going to cover, you can't get electric field.